Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 312, number of good paths. Hopefully you enjoyed my intro drone video of my last week's travel to Ireland. If you enjoyed that, check out my Instagram. There's a link somewhere below in the description. That's as close as an ad as you'll get from here. I just enjoy traveling. Anyway, hope you see that there's a lot of good paths is what I'm saying. This one is actually way tricky. As you can tell by the number of solves, I actually struggled a lot with this one. I took about almost 20 minutes. I actually kind of had the core idea pretty quickly to some degree, but I was missing the way to frame it in my head. And what I mean by that is that, and I'll go over that in more detail in a little bit, but I was just kind of figuring out how to solve it in a let's just say let's go. Let's just do an explanation. Basically, the first idea here is try to the first thing we have to see is the constraints, and given that n is equal to 3 times 10 to the fourth, and we have to do it a little bit faster, right? Because n squared is going to be too slow if you're trying to do, and in fact the answer can be n squared, for example, if all the nodes have the same value, right? So n squared is going to be too slow. You have to do a little bit better than that. You have to do better than than asking, okay, for each thing, let me look it up what other thing, right? Even if you only bucket by the same value, it is not good enough. The core idea that I did come up with very quickly is to process the nodes, right? So the idea here, and let me actually I'm going to do some drawing, so hang on. Let me bring it up on the screen. So basically, let me also just copy this, maybe. I don't know if I'm going to use this, but basically the idea is that given actually that's good, right? Basically, given given I think the tricky part about this problem is putting it all together at the same time. And what I mean by that is a lot of times different algorithms, like you can almost divide the problem into different pieces such that when you solve I think that's what's hard for me in this one, is that you're able to solve piece A and then piece B and then piece C, almost like, A, B, C, and then, you get the solution. Sometimes you're missing one piece. That's fair. But, but for this part, I think it's about just doing one big A, right? Like one big thing for me that is together, which takes multiple components, but they have to interact in that way. Anyway, so the first thing to notice for me is that, okay, I don't know if this is an observation per se, but this is just an idea or a strategy that I was thinking, right? I was thinking that, okay, let's say you have some tree, right? I'm just drawing, just remember it doesn't even have to be a binary tree, but something like that, right? Well, the first idea is that, okay, let's say, this is the final tree, right? But let's say we sort them and we process them one by one. What would that look like? Well, or value by value rather, because of type breaking situations. But yeah, what would that look like? Well, let's say we have then in the beginning we have essentially a disconnected forest, right? Something like that. And then basically what happens as you process nodes is that you basically start connecting nodes, right? Let's say you do, and then here, and I think this part was the insight that I had immediately. But then the question is, okay, now that we have this, what is a good way to get the answer, right? Because I was like, oh, okay, let's say this is value 2 and this is value 2. Well, and that means that everything here now is 2 or smaller. That's basically what we're saying, right? Meaning that as we add edges, the thing that we have to keep in mind is the invariant. And the invariant here is that as we process node values, everything that is connected, everything that is connected has a value that is smaller than the last value processed. And what I mean by that is that let's say we have 2 on here, and that's the last value processed. That means that every other node is either a 2 or a 1 or a 0 or something like that, right? And that means that's by definition of how we did it, by keeping track of the invariant. And then my problem was for a long time, and that this took most of the time that I spent on this problem actually, is that okay, well in this case, how do you do the count, right? Meaning that, like for example, I'm on this node. How do I know, like, okay, maybe there's a 2 here, but this obviously these things don't connect because I don't know. I actually drew this a little bit poorly. I think this has to connect by the way that I drew it, to be honest. So okay, so maybe let me take this back for a second. So yeah, so maybe okay, let's say this one, right? Well, how do you sorry friends, how do you see if these two are connected? Well, and this is something that if you've done enough problems, you'll know that these kind of gradual connected component things are going to be solved using union find. So one thing that is straightforward is that, okay, given these, knowing that this node and this node here up top and this other node on the bottom, we know that they have 2s, but like I said, there could be n squared pairing of these, so you can't really go so you can't really do like an n squared type thing of checking it, right? So it took me a long time, at least a majority of my time spent on this problem. But the idea that I end up with is that, okay, let's say the last number that we process is 2, then here we basically take every node that we just processed and we go, okay, what component am I, right? So this component and this component, say. And then now we go, okay, well, this 2 sees one more 2 in its component, right? And that's pretty much it. We go, here there are 2 nodes that are of 2. So, and of course you do some like n choose 2 type thing. So this is going to be 2 and this is 1, right? If this was a 2 as well, then now this is a 3. Then of course you have a 3 choose 2 type thing, which is you go to 6, right? So that's basically the idea behind how I did it. It actually took me a long time to think about it in terms of the nodes that we just processed. The tricky part for me was that I was thinking about too many different things about the node, but once I kind of think about, okay, these are the nodes that we just processed, so those are the only nodes that matter. And what I mean by that is, okay, actually, let me go back to the drawing. I took it away too quickly. What I mean by that is that now, let's say we go to the future where we're processing a 3, right? Let's say this node is 3. Well, and let's say this node is a 3 as well. And that means that this connects to this, say, and so forth. Oh, I actually drew it a little bit incorrectly, sorry. So that means that this connects to this, and this connects to this, because this is a 3, right? And this node connects to, I don't know, I drew this a little bit awkwardly, but let's say this is a 3 then, right? And this connects. But keeping in mind that now, even though the graph is more connected, the fact that this 2 and this 2 is connected doesn't matter anymore, because that means that now the invariant is no longer true, which is that, or if they're connected, they could be connected with a higher value, which is why that is not possible. So yeah, so now we'll go over the code. This is actually the first time in a Leetcode contest that I copy and paste my own union find code. So this is my union find code. Feel free to use it if you want. Please don't get me in trouble with plagiarization or or whatever. But this is my code. Yeah, I mean, it is what it sounds like. Mostly because in the past I actually am very okay with just like typing it out. But I have made typos in the past, and also I just trying to get a little bit of a good time on the first week back. So yeah. Anyway, so this is the union find. This is just me keeping track of the total you move below. This is me parsing the edge list into an adjacency list. And here, I did it this way so that we can process all the numbers of the same value at the same time. So basically we bucketed things by the value to the index so that we can look it up here again, but also, you know, so that we know what the edges are. And here we process it slowly from left to right, or, you know, from small value to a big value. And then for each index that is in that order, meaning all the things that we bucketed, for each index here, we merge all the, we process the node by merging it with its adjacent neighbors if this is bigger than the neighbor, right? Because if you have let's say you have a 1 node and then you have 2 node, if you process the 1 still doesn't connect to the 2 yet. Only when we process the 2, we process those nodes. So that's basically this idea here. Yeah, and then this is the part that took me the longest part to write, was that, and obviously the code is easy to write per se, but it's about the thinking and the process and getting it correct. So that was the trickiest part for me. Yeah, and here what this is saying is that, you know, for each, I mean, this is just a lookup hash table, and then for each item that we just processed, the same thing that I have here, and this part took me a while. We find the parent, we increment it by the you know, this is just regular lookup list, and then we add the total to that lookup. You can also do it in a couple of other ways where you do what I said before, where for each key of here, you do n choose 2. It's the same thing. So yeah, because you can think about this, the way that this writes out is that this is 1 plus 2 plus 3 plus 4 plus ... plus whatever piece of I is, and therefore it is the same. You could prove it that way. And then that's pretty much it. You return the total at the end, and that's it. Let's put, without going into too much details, let's say that the union find code is constant operations. In that case, this you know, this is linear in the size of the edges. This is linear in the size of the nodes. This is linear in the size of the edges. Just well, except for the sorting, you probably could have done this in a different slightly way, but because of the sorting of the keys, this is going to be n log n. But all this come in an amortized kind of way. All of it combined will be linear in the size of the graph, because each edge gets processed at most twice, one from each side, right? So that means that the summation of these two for loops will just be all the edges together. So that's that, and assuming this is O of 1, this is going to be O of y altogether. Yeah, and this as well, right? Because every node will only get processed once here, so this is also going to be linear time, and here, yeah, like all the nodes will only be in here once, so this is all linear time in total. So everything's just dominated by this sorting of keys. So this is going to be in total. Let me write it on bottom maybe. This is going to be O of n log n time. Well, let me use y notation. Sorry, v log v plus y time. Y because, you know, you have a lot of edges. But I guess actually in this case I lied, because y, this is a tree, right? So y is equal to v minus 1. So this is going to be just v log v. And then in terms of space, this is going to be v space, because we have a lot of linear space e things here. Including union find. So yeah, that's pretty much all I have. So yeah, let me know what you think. Stay good, stay oh yeah, and of course you can actually have some like linear sorting to improve, if you want to say it that way, with some like normalizing the keys and then do a, you know, bucket sort or whatever, right? Some kind of linear sort. So you can improve on it. It's not that practical, if you ask me. Anyway, and that's all I have for this one. Let me know what you think. Stay good, stay healthy. To good. Oh no, wait. Actually, yeah, you could watch me solve it during the contest next, and you could kind of see just like me struggling a bit until the end. So maybe watch on fast forward or something. Anyway, see you in a bit. Okay. Yeah, I misread that one a little bit. We have a tree. We have, what do we have? Okay, let's actually read the problem. You have some values where okay, so I've noticed given the value, edges, the undirected edge. Okay, so a good path is the starting and the end has the same value. Okay, all nodes have less than or equal to the same value. Okay. Distinct good paths. Do we have any mods? I guess it's only n squared, so. But n squared, I guess n. Okay, fine. Let's see. Wow, someone already got it. So probably multiple people got it. But that Q2 mistake may actually be expensive. But okay. So we have a tree. They drew this in a really weird way, to be honest. The nodes, like, why would you not put the, okay, fine. So 1 to 1, 0 to 3. Okay. But 2 is not good, okay. And then you want the 3 to 3 as well. So 3 to 3 is 1. And oh, and then 1 for each node, okay, for itself. I see. Seems like a union find thing, really. Maybe. Let's see, right? Yeah, I think probably 2 people got it. And then we slowly process the nodes together, and then just look at all the connections. Yeah, and then do we have n squared time? We don't have n squared time, so we have to be careful. Yeah. My neighbors are very loud, so if you could hear that, my apologies. So that means that we have to do. No, that should be okay. I see. Yeah. Okay. Let's see. Okay. You got this, Larry. You just have to think about how to do it correctly. Okay. 0 to. And then actually. Not gonna lie, I usually don't copy and paste my code, especially for union find. But I feel like people were telling me that I should, so I've been starting to do it more. So okay, fine. Well, like this is the first time actually, so I don't know. Let me know what you feel about this. Okay. So then now we sort the. Okay, so let's say total is 0 to 0, right? And then return total. Okay, that's silly. But then now we sort the. Okay, enumerate rows, index v in rows, and for this we want to actually sort by re, right? Yeah, okay. Yeah, I think that's fine, maybe. I'm trying to think about the tie-breaking cases, but maybe that shouldn't matter, so okay. Okay. Alright, and then now for re-index and re, what do we do? Oh, I have to sort this first, Larry. Come on. That would be really sad. Okay. We have to, well, when we, okay, let's actually write. This is just double checking that it was index. Okay, that's good. And then now when we parse it, what do we do, right? When we parse it, we how do I say this in a good way? We parse this, well, we put all the edges that are related to it, sure. UF dot union For you, the we is a little bit messy. Okay, for wow, for we in edges of wow, no, edges of index. Wait, what? No, there's just only one thing, right? So for u in edges of index, we want to index and u. Okay, that sounds right. Yeah, okay. And then now, this is going to be n squared if I'm not careful. Now what happens, right? Now that we have another graph and we have to do a query on, okay, this number and looking at every other number. And how do I do this in a good way? If you've started yet. Charge finished already, wow. The one penalty is actually very expensive. But okay. Unless I'm doing it wrong. No, okay, so then now we look at all the things that when it small versus into bigger, maybe. Do I already do small into big? Maybe that's not unifying, then that's just small into big. And then no, you can do small. Okay, what am I trying to do? Basically now, given the value, we want to look up all the values that it is already good with, right? But how do we do that in a good way? That's the tricky part, isn't it? So here, maybe I thought you can, but okay, let's say now we have this, right? How do we say how many of these are connected? Because of the value. Can I use this to look it up in a good way? I don't know, to be honest. Not with our linear type thing. Maybe I'm wrong on this one. Yikes. So we could get the parent. But that's just going to be n squared, right? And that's too slow. It is a tree. Does being a tree help with these giant blocks? We have a set. Because after the union, it's not quite clear. It's small into big enough of a proof. Oh no. What's happening? have to do some magic here in the small and too big. Then it's n times log square n. What's log square n? Don't know if that's fast enough either. Wow, I am lost on this one. A lot of people got it though. How do you look up the people that you care about? Okay, so now this, let's say this changed, right? But you still have to look up all the things that it cares about. What is number of edges? Number of edges will be n-1, but then you can't really look up all the things that are the same, can you? How do you do it? Okay, we process this in this way, but okay, you take a look at every number. But that could also, other values can be of 10 to the 5th, so that's not useful if we need to break it down and then do a merge type thing. Because they can be at n square no answer, right? So n square node, so you have to do a little bit faster than just doing a lookup. I don't know how to do it though. Also, this may be wrong anyway, because I think if they're all the tie breaking may actually do things in the wrong order for the check, so I have to handle this a little bit differently, but okay. Okay, let's say we have a tree that is disconnected forest. Then what does that mean when we pass a node and all the nodes at the same time? Okay, let's say we update the state, and then now, but then now, I see. Okay, I think I have the idea. I think this is maybe okay. Okay, let's see. Okay. Let's see here. Whatever. Let's say we again index. Okay, right. And we have some. And now what? Okay. Yeah. Okay. I think I see it now. Maybe. We'll see. And then now sorted order keys for in. And then now we do all the union find together. Okay, for index in order of re, so that's just a value. Then now for u in edges of index, we want to do this union find. Okay. Right. And now we just do the count, right? which is for index in order of we go okay. Just say p. So then here we go parent p of uf of find of index increment by 1, and then total we add this number. I think that's it, maybe. Don't know if that's true actually. Well, maybe with the syntax a little bit better. What? Oh, it's E sub index. That's wrong. That's good that is wrong, I guess, because then now I don't have to waste the wrong answer to find out what the real answer is. But why? Index and then okay, so 0, 1, so 3. Well, that's the index 3. That's the other one. Has 2. Is that true? Wait, is that true? No. Oh, I see. Because it thinks that I'm connecting it wrong. What I need is if rows of u. So when we pause this file, we don't do the edge unless this is the bigger one. Okay. Is something like that? Or just we, I guess. Okay, well, I don't know if this is right, but it's giving me at least right answer for the inputs, which is not bad, but yeah. We do a micro optimization. Maybe I don't need it, but alright, YOLO, please. Cool. Silly mistake on Q3, I misread it. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, this problem, and everything, you know, on this thing. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.